we have Mr. RMPS Bandara for the third presentation. He's a lecturer from the Mechanical Engineering again of KDU. He's going to talk on modeling of conventional swing of the cricket ball using computational fluid dynamics. His work is also jointly with Mr. NS Rathnayaka.
Thank you, Madam. Chairperson, Professor Dayavansa, distinguished invitees, ladies and gentlemen, good afternoon to you. The title of my presentation is Modeling of Conventional Swing of the Cricket Ball Using Computational Fluid Dynamics. This is jointly done by myself, I am Priyantha Bandara, and Mr. Nimal Rathnayaka. I have organized my presentation according to these titles. Initially, I will talk about, I will give you some overview on the topic, then the research objectives, governing principles, governing equations, methodology that I have used in this particular study, then the simulation results, and finally the conclusion. So let me elaborate you on the overview. As you know, cricket is a sport that is capable of attracting many spectators around the world to many stadiums. And not only to the stadiums, but they can also watch the cricket matches live on many different coverages. And especially in the Indian subcontinent, this is considered to be not just a sport, but rather like a religion. So I hope you can remember in 1996 when we won the World Cup. I mean, throughout the country there were bombs getting exploded by the LTT, but still the country got together to celebrate the event in a grand scale. And also when our own Muthaiya Muralidharan was snowballed by the umpire Darrell Hare and Ross Emerson in Australia, not only Captain Arjuna Ranatunga, but the whole nation stood behind him, supported him, tried to save him. So this is not just a sport, but it's rather more than a sport. And also the beauty of this sport lies when the bowler and the batsman try to dominate each other for supremacy, to take advantage of the other. So fast and medium fast bowlers in cricket actually use different strategies to defeat batsmen in a cricket match. There are different strategies or armory that the bowlers use, like air swing, seam movement of the pitch, the bouncer, yorker, etc., which you are already familiar with. And if you take air swing of the ball, there can be three categories: the conventional swing, the reverse swing, and the contrast swing. So actually during this study I am going to confine myself only to conventional swing. So what is conventional swing? Conventional swing takes place when the cricket ball is new, especially at the beginning of an innings of a cricket match, when the ball is new and when it is delivered at an angle to the line of delivery to the batsman, and during the flight it moves in the direction of the seam orientation. There should be an angle between the seam and the line of delivery, so that during the flight it will deviate from the line of delivery. So actually previous studies have been done to understand and analyze this particular phenomenon, mainly through experimental techniques, but they have their own drawbacks, limitations, and the results are not that accurate, mainly due to the experimental errors that are involved. So my research objectives is to analyze this particular phenomenon, that is the conventional swing of the cricket ball, on the context of computational fluid dynamics, or CFD for short, with respect to angle of seam of the cricket ball and the speed of delivery. And also, secondly, to make recommendations for optimizing the conventional swing so that the bowlers can make use of this particular weapon to defeat batsmen. If you take any engineering problem, there can be three solutions. One is an analytical solution, then you have a numerical solution, then you can have an empirical solution or experimental solution. Of course, if the problem is fixed and if it is simple, you can use your fundamentals and you can generate an analytical solution. But for all problems, you cannot find analytical solutions. Then you have to go for numerical solutions. For numerical solutions also, there can be manual solutions, and also sometimes you cannot obtain manual solutions because the governing equations are so complex. Then you have to go for computer-aided solutions. So this particular problem fall into computer-aided numerical solutions. Of course, you can have empirical solutions also with experimental techniques, but it takes time and it consumes a lot of money. So these are some of the governing principles that will govern the movement of the cricket ball in its flight. So here you can see we have basically the seam at an angle. This is the primary seam, which is playing a great role on conventional swing. So it is at an angle to the line of delivery. So the velocity is u, and these are the flow parameters. Then when this is delivered, then there will be air resistance. Because of that, there will be a drag force in the opposite direction. And because of this seam, later I will explain why this is happening. There will be an side force also acting on the ball. And normally the bowlers keep one side smooth or shiny, the other side rough, just to facilitate this conventional swing. So depending on the conditions at which you bowl, there can be drag forces, lift forces, and side forces. Lift force is perpendicular to this screen. Especially if the ball is rotating while it is being delivered, then you can have a side lift force also in addition to drag force and side force. And all these are governed by the Reynolds number. It will decide whether the flow is laminar or turbulent. So these are the basic governing principles. And the flow physics are very complex, and basically Navier-Stokes equation, which is comprised of continuity, momentum, and energy equations, are integrated into the system. And then you have directions in the equations can be written in the x direction, y direction, and z direction. So these are the governing equations which you cannot solve them manually. So it's quite difficult. So that's why we need a computer to get this solved. The most important thing is turbulence. Turbulence is very difficult to model. You cannot predict turbulence. There are different turbulence models. The most popular model is the standard K-epsilon model, which is introduced by Lond and Spalding. But it has many applications in the industry, especially where complex flows are involved. So here we have two parameters, K and epsilon, which is the turbulent dissipation rate and turbulent kinetic energy. K is turbulent kinetic energy, E is turbulent dissipation rate. And also you have set of constants. So these are the two basic equations to model turbulence. And then once all the governing equations are incorporated into the system, you have to make use of your computer to do the to solve all the equations. So this is the methodology that I have basically used. First, I developed a computational model for this problem. So this is a complex flow problem. Although it seems simple, it is not so simple because turbulence is involved. I used one software which is known as Gambit, which is very well validated for these kinds of applications. It's a solid modeling software which you can develop solid modeling computational domains. And you have to incorporate boundary conditions and the physical geometry of the ball. And then you can generate a mesh. The mesh points will assist you to solve all transport equations throughout the domain. And then once the computational domain has been created, you can export it as a mesh file to your main software, which is the CFD tool, Computational Fluid Dynamics tool. And this is a commercial software which I have used. It is known as ANSYS Fluent 6.3. And again, you have to incorporate the boundary conditions, the flow properties, the turbulence models, and all other models applicable so that you can run your simulations, and then if your simulation is successful, then you can generate a converged solution. So this is not so easy, because in the middle your simulation can crash, and sometimes there will be stability problems. So you have to make sure that you finally obtain a converged solution. So when you do that, you get numerical data, graphics, and different kinds of plots available at your disposal. And if you don't get a converged solution, you have to go back and you have to look where you went wrong in the computational model. So you have to keep looking for a realistic solution, converged solution, until you get what you desire. These are the modeling parameters that I have used. Diameter of the ball, these have been selected as per the rule number 5 that has been introduced by the International Cricket Council, ICC. 72 millimeter diameter, width of the primary seam 20 millimeters, projection of the seam from the ball surface is just 1 millimeter from the surface, mass of the cricket ball 0.16 kilograms, roughness height, of course the roughness height changes from one place to another, so it's very difficult to get one surface roughness value, but in most research papers they have used 0.3 millimeters, and also we managed to experimentally measure some of these roughness values. So basically we got 0.3 millimeter roughness value for this study. Dimensions of the computational domain, we basically got a rectangular domain of these dimensions, parallelepiped. Type of mesh and number of node points, triangular volume measures were used because they are very stable and easy to analyze also. So it had 2.2 millimeters